Let's dive right into this explainer and deconstruct exactly how Cobalt Strike Beacon manipulates memory to hide. If you're a security analyst focusing on detecting malicious memory patterns, understanding these mechanics is absolutely critical. We're going to break down the cat and mouse game between attackers trying to blend in and defenders trying to spot the anomalies. By the end of this, you're going to know the precise anomalies you need to be hunting for.
We've got a clear forensic roadmap for today. 1. The memory scanning battlefield. 2. The RWX memory trap. 3. Hiding with module stomping. 4. Blending post-X processes. And finally, 5. Hunting string artifacts.
All right, part 1, the memory scanning battlefield.
Let's start with the stakes in our detective story here. What happens when an attacker fails at OPSEC? Well, a defender alert pops up, and you might notice an MSS postfix at the end of the threat name. That MSS tag means a memory scan caught their beacon shellcode loader settling into memory. Because let's be real, each payload artifact, whether it's an exe, a DLL, or a PowerShell script, does the exact same thing. It injects beacon shellcode, resolves imports, processes relocations, and starts running in memory. When antivirus products run the routine memory scans or trigger them based on suspicious activity like new threat creations, they can catch beacon red-handed.
Moving into part 2, the RWX memory trap. So let's look at the very first hurdle attackers have to overcome to avoid triggering those specific alerts. Default beacons allocate a glaringly obvious RWX memory block. That's execute, read, and write. Most native applications just do not use RWX memory, so it's a massive red flag for any defender. But attackers can camouflage this by setting a specific configuration in their malleable C2 profile called stage.userRWX to false. They force the loader to change its behavior entirely, allowing it to blend perfectly into normal RW and RX blocks.
Attackers know that RWX memory is a total trap, so they force their loader through 3 very exact steps to mimic legitimate application memory permissions. First, it allocates memory with just read and write permissions. Second, it copies the beacon into that memory. And third, it loops over each DLL section and sets the final memory permissions according to the section characteristics. So the text section becomes RX, the RData section becomes R, and the data section becomes RW. This severely complicates your memory scans, because suddenly it looks completely normal.
That brings us to part 3, hiding with module stomping. Now, you might be wondering, once they've stripped away the RWX indicator, how do they hide the actual executable code from your analysis? It's a great question. Attackers will often set stage.copy_PE_header to false. This prevents the loader from copying the DOS and NT headers, literally leaving only the .text and .data sections sitting there in memory. It completely removes the obvious signs of a running portable executable. But as analysts, we can still catch them by looking very closely at how that memory is backed.
Usually when you review RX memory regions associated with a loaded PE, you're going to find that they are all backed by a legitimate module on disk, because, well, that's where they were loaded from. If you're using a tool like System Informer, you can look under the Use column and clearly see the legitimate disk files backing those memory regions.
If an RX region isn't backed by a file on disk, boom, there's your anomaly. That's your unbacked memory indicator. However, advanced attackers counter this using a technique called module stomping, or module overloading. By using the stage.modulex64 option, they tell the loader to map a large legitimate PE from disk, like hydrogen.dll from the system32 folder, and then simply overwrite its memory with the beacon later. The end result? Beacon's PE appears to be perfectly backed by a legitimate module on disk, completely bypassing your unbacked memory detection.
All right, part 4. Blending post-X processes. Let's see how this evasion mindset applies when Beacon actually starts doing the heavy lifting of post-exploitation. As a blue teamer, you can think of command behavior like a cheat sheet. Cobalt Strike has different classes of commands with totally different OPSEC footprints. Housekeeping and API-only commands, they're relatively quiet.
Inline commands, executed as beacon object files, run right in the main thread and avoid new thread creations entirely. But fork and run commands like execute assembly or powerpick, those carry an absolutely massive offset burden. Why? Because they literally have to inject shellcode to start a new thread or spawn a completely new sacrificial process. Knowing this tells you exactly where to look for injection events.
Just think about the stark contrast between lazy OPSEC and advanced evasion. Imagine an HTTP beacon running inside Microsoft Edge. If it lazily spawns a command shell, you see msedge.exe spawning cmd.exe. That is a glaring red flag. Edge shouldn't be spawning command prompts. But with the advanced approach, the attacker uses the ppid command to spoof the parent process ID. Now, cmd.exe appears to be spawned by explorer.exe instead. Suddenly, that whole process tree looks entirely legitimate and seamlessly blends into the surrounding environment.
Attackers lean heavily on specific configuration blocks in their post-ex and process inject setups to maintain this illusion. They use spawn2 to dictate exactly which programs to use as sacrificial processes, dodging suspicious defaults. They use PID to spoof those parent-child relationships, just like we talked about. They use AMC_disable to actively patch AM size straight out of memory. And they carefully tune process inject to control exactly how threads are created, sometimes even spoofing the starting address of a thread to point to a legitimate function like RTL user thread start. For an analyst, this means you absolutely need to monitor for spoofed relationships and unexpected thread creations pointing back to unusual shellcode.
Which brings us to our final section, Part 5, Hunting String Artifacts.
Let's look at the last breadcrumbs left behind in our detective story here. Strings. Even when the memory is camouflaged and the processes are perfectly spoofed, the code itself often gives the attacker away. Hard-coded strings in the PEs.rdata section are a common culprit for memory-based detections. Dumping the raw beacon DLL memory will often reveal hard-coded format strings used for everyday commands. I'm talking about specific %s and %d combinations used to format date and time output for the ls command or output for getuid. Attackers know this, of course, so they try to scrub these indicators using malleable C2 strum rep commands, substituting raw bytes or transforming strings to evade your Yara rules. But here is the ultimate gotcha, and honestly, it's a bit of poetic justice for defenders. Attackers cannot blindly replace all strings without breaking their own tools. Beacon has an internal web server used for workflows like PowerShell import, where a third-party script is hosted internally and downloaded into a run space. If an attacker gets a little too aggressive and uses strrep to replace strings like http:/1.1/200OK, they accidentally make their own HTTP responses non-compliant. This completely breaks their post-exploitation workflows. So they are literally forced to leave these standard HTTP strings in memory, giving you a persistent, unbreakable artifact to hunt for. So, this cat and mouse game, it never really ends. Attackers are going to keep tweaking their malleable C2 profiles. They'll keep stomping modules and spoofing PIDs. But by knowing exactly what memory structures they are forced to modify, and more importantly, what internal mechanics they absolutely can't afford to break, you can always pick up their trail. So I'll leave you with this question. Next time you're analyzing a memory dump, are you just looking for the obvious RWX traps, or are you hunting for those subtle, unbreakable artifacts they inevitably leave behind? Thanks for joining me on this explainer. Keep hunting, and I'll catch you next time.